Greetings. Welcome to the Infinite Series lecture number 3. In the previous lesson, we have learned how to find a series whether it is convergent or divergent by using comparison test method. But in this lesson, we learn the same but in another method, what we call Cauchy's ratio test or D'Alembert ratio test. Let's just start. If we have a series and we have an infinite series and we have to find whether the series is convergent and or the series is divergent, we have to find some method. We already have learned about the comparison test, but in here we learn one more test to find a infinite series is convergent or the series is divergent. Let's take first an infinite series n tends to infinity un. This is an infinite series. Now we have to tell or we have to find that this series is whether uh, convergent or this series is divergent. To find this series convergent or divergent, we'll learn here one another method that is called Cauchy's or D'Alembert ratio test. Okay, this test is called Cauchy's test and or D'Alembert ratio test. In that particular series, basically we measure the rate of growth or the decline of a series, so that if that growth is, if we find that the series is growing, then we will call that is divergent, and if it is called it is declining, then we will call it is that the series is convergent. Okay, now how can we find that method, that whether it is growing or declining, how we will find it? This for this we have to find a limit L is sum of n tends to infinity. Okay, we have to find this by un. Now for the growing, for an growing things, if the series is growing, then that will be more than 1, and if it is not growing, if it is declining, then this series this L will be less than 1. And for one case, if it is not growing, neither growing neither declining, then that L is equal to 1. Okay, we find that ratio, this ratio we have, this ratio will tell us that if the series is convergent or divergent. For this scenario, that series is divergent, but for this scenario series is convergent, because the series the series is declining, so it is the convergent series. Okay, and another case, if L is equal to 1, then what will I say? Then we can say it that the test fails, as we don't get anything inconclusive from the test, so we can say the test is failed. Okay, let's take an example of that ratio test. Okay, we have a series. This series we have to find whether that series is convergent or divergent. The first thing is what we have, that un is equal to, we can write that n by 2 to the power n. So we can write u n plus 1 is equal to n plus 1 by 2 to the power n plus 1. So we can write this as the limit of, we can find that limit that n tends to infinity as u n plus 1 by u n. So that can be written as n plus 1 by 2 to the power n plus 1 into this, that is in downside, so we can write it by 2 to the power n by n, that. Okay, that can be written as 1 by 2 n plus 1 by n, that also can be written as 1 by 2. Now if we do this in that, that can be written as 1 plus 1 by n. Now look at this, for this n tends to infinity, this term will be tends to 0. So for that limit, for this n tends to infinity, what we get is 1 by 2, 1 by 2 for limits gain that is less than 1. Okay, that's so the so therefore the that is less than 1, so the series is convergent. So what can I say? That series is, this series is con convergent. So the series is convergent. Okay,